Okay, let us go for the next topics of our course. So we are studying differentiability of functions, and now we go for algebra of the derivatives. So this is the topic. And so again, we want to give rules for the differentiation of sum and products of differentiable functions. So the hypothesis is that here we have f and g, two functions defined on an interval that can be taken to be open, and x bar in AB, and fg differentiable at x bar. Then the first rule is the following: the sum of the two functions f plus g is differentiable to at x bar and f plus g prime at x bar is equal to f prime of x bar plus g prime of x bar. Okay, so the proof. Again, we look at the increment of f plus g, so we compute f plus g of x minus f plus g of x bar. Of course, this is f of x minus f of x bar plus g of x minus g of x bar. Okay, and this is equal to what? The increment of f is f prime of x bar times x minus x bar plus little o of x minus x bar plus, here the other term is g prime of x bar, sorry, g of x bar. No, it is g prime of x bar, x minus x bar, plus little o of x minus x bar as x goes to x bar. So here we have f prime of x bar plus g prime of x bar times x minus x bar plus little o of x minus x bar as x goes to x bar. So notice that here we reconstructed the definition of differentiability. So the increment of the function is decomposed into one term which is proportional to the increment of the variable plus a term which is an infinitesimal of higher order. So this is exactly the definition of differentiability. So we have f plus g differentiable at x bar, and this factor here is the value of the derivative. So again, this is exactly what we wrote. F plus g is differentiable at x bar, and f plus g prime at x bar is equal to f prime of x bar plus g prime of x bar. Okay, I prefer to give you the proofs of the algebra by using the little o's first, because in my opinion it is clearer than just doing a limit. You really see an idea of expansion of a function. Okay, there is a linear part and then something which is higher order, which is negligible with respect to the linear bar as x goes to x bar. Second, because so you get trained in the use of this new language. So the second rule is about fg. So we have that also f times g is differentiable at x bar, and fg prime of x bar is equal to f prime of x bar g of x bar plus f of x bar g prime of x bar. This is called the Leibniz rule. Okay, and notice that here, if you never saw this result, this sounds at first a bit puzzling, because you are used to the fact that the limit is linear. The limit of the sum is the sum of the limit of the product is the product of the limit. So since the derivative of a limit, you expect that the derivative of the sum is the sum of the derivative, and this is the case indeed, but also that the derivative of the product is the product of the derivative, and this is not the case. Okay, by using this little law language, it is very easy to understand why. So again, we start with the increment of f times g. So we have fg of x minus fg of x bar, and this is equal to f of x g of x minus f of x bar g of x bar. And here just use the definition of differentiability for f and g. So here you have f of x bar plus f prime of x bar times x minus x bar plus little law of x minus x bar times g of x bar plus g prime of x bar times x minus x bar plus little law of x minus x bar. And this is fg because this is f and this is g. So here we have, this is minus f of x bar g of x bar. And so you get here f of x bar g of x bar, it is the first term that will be cancelled by the last one. Then you have plus f of x bar, and here g prime of x bar times x minus x bar, plus again f prime of x bar g of x bar x minus x bar, and all the rest here is a little law of x minus x bar that multiplies all this stuff. But when a little law multiplies all this stuff, everything remains little law of x minus x bar. And the same here when this little law multiplies all this guy here. So we have here plus little law of x minus x bar minus f of x bar g of x bar, cancelled by the first term here. So let us go on and just collect factor x minus x bar. So here you first have f prime of x bar g of x bar plus f of x bar g prime of x bar times x minus x bar. And what remains here is a little of x minus x bar as x goes to x bar. So as before, okay, we have that then by definition of differentiability, then we have that f times g is differentiable at x bar 2 and Leibniz rule holds. So fg prime at x bar is equal to f prime of x bar g of x bar plus f of x bar g prime of x bar. And this is the end of this proof. Then, as a corollary, it is important here to give you this corollary as a corollary. Consider number c, a real number c, then the function c times f is differentiable at x bar, is differentiable at x bar. And c times f prime at x bar is equal to c times f prime of x bar. Okay, proof of the corollary is immediate. So like we did for the proof of the limit of CF, here we define another function g of x is equal to c. So g differentiable at x bar, because it is a constant function. We already had this example at the previous lecture. So g is differentiable at x bar, and we know that g prime of x bar is equal to 0, constant function, has 0 derivative. Therefore, cf prime at x bar is equal to gf prime at x bar, which is f prime of x bar g of x bar plus f of x bar g prime of x bar by previous lemma, so Leibniz rule. But g of x bar is equal to c, and analogously g prime of x bar is equal to 0. So at the end we have c f prime of x bar, end of the proof. And now the last rule of this, no, it's not really the last rule, the second last rule of this algebra is, about the ratio of two functions. So here we have to introduce another hypothesis. So the third theorem here says that if, moreover, g of x bar different from 0, g prime of x bar can be equal to 0. The important fact is that g of x bar is not 0. Then f over g is differentiable at x bar and f over g prime at x bar is equal to f prime over g at x bar minus fg prime at x bar divided by g squared at x bar. Perhaps you are more used to see this rule in the following way. This is f prime of x bar g of x bar minus f of x bar g prime of x bar divided by g squared of x bar. Okay? And sometimes it is much more comfortable to use this form. However, so let us go for the proof. It is another computation in as in the usual way. And so we start by computing the increment of the two. So we have I write here proof. We have f of x divided g of x minus f of x bar divided by g of x bar. This is equal to f of x g of x bar minus f of x bar g of x divided by g of x g of x bar. Now we use differentiability here and continuity here. So first we look at the numerator, and here we have f of x bar plus f prime of x bar x minus x bar plus Lido of x minus x bar. And this is just the first factor here at numerator, and we do like this, and this is g of x bar minus f of x bar, and we expand g of x, and g of x is g of x bar plus g prime of x bar times x minus x bar plus Lido of x minus x bar. And again, here we have g of x bar. Okay. And so now develop a bit this expression. You immediately see that one has to cancel here f of x bar times g of x bar, and the other term is minus f of x bar times g of x bar. So here we have f prime of x bar g of x bar, here it is good, times x minus x bar, but there is another term here which is sorry, here I canceled this guy here, but I had to cancel the other guy here. And the other term here that is proportional to x minus x bar is f of x bar g prime of x bar x minus x bar. So, and there is a minus sign in front, so here minus f of x bar g prime of x bar times x minus x bar, and everything here at numerator is Lido of x minus x bar, okay, plus Lido of x minus x bar divided by g of x bar. Okay, g of x bar, let me write this note that moreover, since g differentiable at x bar implies that g is continuous at x bar, and g of x bar is different from 0, we have that the inverse of g of x bar by discontinuity can be written as 1 over g squared of x bar plus Lido of 1 as x goes to x bar. Then, going from the very beginning, we have that this difference, this increment of the function f over g, so f of x divided by g of x, minus f of x bar over g of x bar, this is equal to what? Here, we repeat this numerator here, so I write it exactly as it is. It is here, and no fraction, but just another parenthesis here, times 1 over g square of x bar plus little o of 1. These little o's are for x going to x bar. So here we have to multiply, and so this is equal to, let us pass to red color, so f prime of x bar, g of x bar, minus f of x bar, g prime of x bar, times x minus x, sorry, let us cancel this. It is better to write it like that. Here we write divided g square of x bar times x minus x bar. Okay, this is the first term of the first bracket multiplied by the first term of the second bracket. Then here we have little o 1 that multiplies this stuff. This stuff has a factor x minus x bar, so little o 1 times x minus x bar gives plus little o of x minus x bar. And the last term, so the second last term is this little of x minus x bar times this guy here, which remains a little of x minus x bar, and it is already here. And the very last term is elementary because little o 1 times little o of x minus x bar. You remember the algebra of the little o's. This is little o of x minus x bar as x goes to x bar. Again, for the increment of the function f over g, we have a path which is proportional to the increment of the variable plus a higher order infinitesimal. So, therefore, and the thesis that was that f over g is differentiable at x bar, and f over g prime at x bar is equal to f prime of x bar g of x bar minus f of x bar g prime of x bar divided by g squared of x bar. And now the last rule, the fourth, that concerns another operation which is the composition of functions, okay? The composition of functions, the hypotheses are a bit different. However, you have that f differentiable. Let me skip the hypothesis on the domain. They are in some sense implied, but the hypothesis that I'm doing uncomposed differentiability, so f is differentiable at x bar. G differentiable at f of x bar. Then the composition of f and g is differentiable at x bar. And G composed f prime of x bar is equal to G prime at f of x bar times f prime of x bar. Okay, so the proof is as follows. Again, look at the increment of the composition of f and g at x minus composition of f and g at x bar. By definition of composition, this is g of f of x minus g of f of x bar, which is equal to, since g is differentiable, so here I write down the hypothesis, g is differentiable, we have that this is g prime of f of x bar times f of x minus f of x bar plus little o of f of x minus f of x bar as f of x goes to f of x bar. Okay? And now here we have this guy here to be differentiated, and so we use the fact that f is differentiable too. So here we have g prime of f of x bar, and now we have f prime of x bar times x minus x bar plus little o of x minus x bar, and again plus little o of f of x minus f of x bar, and here we can write as x goes to x bar because f is continuous. Indeed, f is continuous. So x goes to x bar implies f of x goes to f of x bar. Okay, so this is a little o as x goes to x bar too. And so now our claim, what we want to prove, is that little o of f of x minus f of x bar is a little o of x minus x bar as x goes to x bar. And how can you prove this? But very simply, using the definition of little o. So little o of f of x minus f of x bar divided by x minus x bar. Use differentiability of f, so this is little o f prime of x bar, x minus x bar, plus little o of x minus x bar divided by x minus x bar. Now remember the strategy how to deal with the lead laws. So replace the denominator with the argument of the lead law. So here you have f prime of x bar times x minus x bar plus lead law of x minus x bar, and then complete the computation, and here you have f prime of x bar times x minus x bar plus lead law of x minus x bar, and here x minus x bar. So here you immediately see that this second term goes to f prime of x bar by principle of negligibility, and this goes to 0. So everything here at the end eventually goes to 0. And so if since this goes to 0, then we proved the claim. So the claim is proved. By proving this claim, we have that this last lead law of f of x minus f of x bar indeed is a lead law of x minus x bar. So we go on, therefore, the composition of f and g at x minus the composition of f and g at x bar is equal to what? So stay here, g prime of f of x bar times x minus x bar, and then here you just have a lead law plus lead law of x minus x bar as x going to x bar. So again, we have that the increment of g composed f is equal to a linear part plus lead law. And be careful to this formula, then we will have some examples of that. So the theorem is proven. And so perhaps we can also add another rule. Let me, yeah. So, and the fifth rule of this algebra is the derivative of the inverse function and here we have that f from AB to R is differentiable at x bar and invertible. We use the notation g is equal to f to the minus 1, namely, for every x in AB, we have that g composed f of x is equal to x, and for every y in the range of f, f of g of y is equal to y. Okay? Moreover, we require that f prime of x bar is different from 0. Then, denoted by y bar equal to f of x bar, g is differentiable at y bar, and g prime of y bar is equal to 1 over f prime of x bar. Proof. Now f is differentiable at x bar we have that f of x minus f of x bar is equal to f prime of x bar times x minus x bar plus little law of x minus x bar for x going to x bar. Use this notation, quite standard. Y is equal to f of x. So this is true if and only if x is equal to g of y. Okay, then we have that y minus y bar. This is this is what? This is f of x minus f of x bar, and so it is, as we wrote before, f prime of x bar. Now x minus x bar here becomes g of y minus g of y bar. Plus little law of x minus x bar as x goes to x bar. So now dividing by f prime of x, f prime of x bar, that has to be different from 0. We required it here. And then we take this g of y minus g of y bar and put it in evidence. We gain g of y minus g of y bar is 1 over f prime of x bar times y minus y bar plus little law of x minus x bar as x goes to x bar. Okay? And the claim I want to show that little law of x minus x bar as x goes to x bar is also little law of y minus y bar as y goes to y bar. So we have to show that little law of x minus x bar divided y minus y bar goes to 0 as y goes to y bar. This is what we have to prove in order to have this statement here. And this is quite easy indeed. As usual, little law of x minus x bar divided by y minus y bar is equal to little law of x minus x bar divided by x minus x bar, and here we have x minus x bar divided by y minus y bar. And so here we have that little law of x minus x bar divided x minus x bar times x minus x bar divided by what? And this is f of x. This is f of x bar. So here we have f prime of x bar times x minus x bar plus little law of x minus x bar. So as y goes to y bar. Now y goes to y bar. This is true if this means f of x goes to f of x bar. This implies g of x, of f of x goes to g of f of x bar, since f is continuous at x bar and g is continuous at x of f, and this is true if and only if x goes to x bar. So y goes to y bar implies x goes to x bar, and if x goes to x bar, then we have that this guy here goes to 0, and this guy here goes to 1 over f of x bar. So the product goes to 0, and the claim is proven. It seems to be complicated, but it is really elementary. So, now, the point is, what we proved in the claim is that little of x minus x bar is a little of y minus y bar, so we can replace little of y minus y bar. Then, starting again from this asterisk equality, we have g of y minus g of y bar is equal to 1 over f prime of x bar times y minus y bar plus little of y minus y bar as y goes to y bar. And this is the end. This is the end of the proof, because we decompose the increment of g into a part which is linear in the increment of the variable plus a higher order infinitesimal. So the theorem is proven. Okay, and this is enough for the algebra of derivative, and the next part we will give some example of computations of derivative. Okay.